welcome. This is HTTP 3. I am Daniel. I work for Wolf SSL. I do curl every day, all day, as much as possible. Some of you might have used it at some point in time. But anyway, HTTP started back in that period, roughly. It looked like that. When we did HTTP 1, that RFC was shipped, the first one in 1996. It was revised a few times. And then we did HTTP 2 a few years ago. I was actually here at Øredev 8 years ago and talked about HTTP 2. It feels like an eternity ago. And now I'm here to talk about HTTP 3. A lot of numbers, fun stuff. But you know, HTTP is that cool protocol we're all sort of accustomed to. We know how to do that. You know, you send a GET, you get send a few headers, you get a response, 200 headers, body, blah, blah, blah. You've seen this. You've all used it. It looks like that today as well. And HTTP, of course, started out over this trusted old protocol we call TCP. You remember networking 101, TCP, like a chain, right? You set it up over IP. It's a connection. You send data back and forth. There's this three-way handshake, ping, pong, ping, to set it up. And you know, if a package is lost, it gets resent. You know, it's a sort of established connection. You know that the byte arrives in the other end in the same order, or not at all if the connection is broken. And it's all in clear text. You know, the first RFC published in 1981, right? So that's 42 years ago. A trusted old protocol. It's actually amazing that it still works as good as it does. But okay, that's TCP. There are many more seats over here if you want to just squeeze in, or if you prefer standing, stay. But anyway, these days we're all doing HTTPS, right? Which means that we add TLS on top of TCP. And TLS, of course, adds security, and we do HTTPS. And I just wanted to show you this little data from Firefox that shows that pretty much everything is done over HTTPS these days on the web, right? Back in 2014, not so much. Nowadays, somewhere in the 90–95% of all traffic. So yes, so we want HTTPS over the web. HTTPS uses TLS on top of TCP, so we add security on top of that, and we use that for HTTP 1 and HTTP 2. It has a layered security, right? So it's privacy and security. We know that we're talking to the correct server, and there's no middleman interfering, and there's no one snooping on the traffic. And there's an additional handshake. We had that 3 ping, pong, ping first, and then we add ping, pong, ping, pong, ping a few more times before we have a connection. You know, a lot of ping pongs. And every ping, you know, is a potentially a long time. But yes, privacy and security, good stuff. We want that. So this is how it looks like, right? Remember? So we have IP, we do TCP, we add TLS, and we speak HTTP. Right, easy peasy. That's the way we do HTTP over TCP. So we started with HTTP 1.1. No, we didn't start with 1.1. We actually revised it with the 1.1 in 97 because 1.0 wasn't good enough, so we did 1.1. Because 1.0 had sort of deficiencies. We couldn't reuse connections. Oh, stupid, we should reuse connections much faster instead of closing and creating TCP connections all the time. Reuse them. Awesome. So we did that so we could do more faster. But it was always done then serially, so we got one by one by one by one, and a modern website has a lot of objects. You don't want to go and get them one by one by one. You want to do them many at any particular time, so you did a lot of parallel connections instead, so you could get a lot of parallel transfers. A lot of parallel transfers. But that turns out to be a really, really inefficient TCP use because you have to create so many connections to make that parallel transfer, so you never really get up to speed on those TCP connections because TCP is slow in the beginning, always. So by creating a lot of TCP connections, they're always slow. And by having so many, you have to close them all the time too when you go to the next site because you cannot keep hundreds and hundreds of TCP connections per tab, right? So you have to close them all the time. So pretty much crappy way to do TCP. So HTTP 1.1 is really not a very efficient way to do web of today. And then we have this HTTP head-of-line blocking problem. That means that you have a finite number of connections to a website, typically 6 per hostname. So what if you want to download 200 images over those 6 connections? So you have to have those 6 sort of lines in the supermarket, and you know which line is going to be the best one for the next request. Really difficult challenge. Sometimes suddenly the request ahead of you is slow, so the next one is going to have to wait to the previous one. A complicated issue. So you have the previous HTTP request could block the subsequent ones. Difficult. So we've done numerous fun workarounds on the web around these problems for HTTP 1.1. And that's a lot of those, when we said, they became the reasons why we did HTTP 2. Because sort of, why do all those workarounds? We can instead improve the protocol so that we don't have to do all those funky workarounds. We can put them into the protocol and make it better so we can do it better for everyone. So we stream, fun. Okay, so it shipped in 2015. I was here, talked about it then. So now the point is, or the idea, the theory is that we use 1 connection per host instead of 6. And we do parallel streams over that single connection, right? And now we can do hundreds of streams over a single TCP connection. We don't have to tear it down all the time. And a TCP connection can get up to full speed, and we can keep it saturated. More data, more speed, faster. It's the idea. But then instead, we ran into another problem, which is called the TCP head-of-line blocking problem. If you do 100 streams over a single TCP connection, and you lose one of those IP packets, suddenly you have to pause 100 transfers, waiting for that single IP packet to get retransmitted, and then 100 transfers can continue, and you lose another packet, then they all wait, and they get it, and then it can continue. So one TCP connection is not ideal either when the connection is bad. And on top of this, we have this awesome effect called ossification on the internet. And this thing with the internet is that it's full of boxes. You didn't know that, right? Woo! And all these boxes, you know, these kind of boxes, routers, gateways, firewalls, load balancers, everything. When the people who owns these boxes, you know, operators, ISPs and stuff, they get these and they put these boxes into the network to manage all that stuff. And they basically never get upgraded again after they are installed in the system, which means that they all know how the network worked at the time the box was put there, you know, 5 years ago. And how did the network work 5 years ago? We don't know. I mean, in the edges, in your browsers, I mean, it upgrades pretty much every time you start it, you notice that it's upgraded again. And even our servers, we actually upgrade them at least sometimes. I mean, every year, twice a year at least. But these boxes in between, basically never. They understand the network from back then. And by not understanding the current way of, I just wanted to illustrate, of course, that that's me and that's the website, and all those in between are boxes, stupid boxes. They know stuff. And because they know how things work, right? So when you speak TCP on port 80, that's old style of saying, yeah, that's how we introduced HTTP once. TCP on port 80. But all these boxes, they know that that's not only HTTP. They know that it's HTTP 1.1 because they help us do that. So if you try to speak something else over the network on port 80, a lot of those boxes will sort of help you do HTTP 1.1. But if you don't speak 1.1, it'll just ruin your traffic. So it's pretty much impossible to speak HTTP 2 in clear text over the internet because so many boxes will help you. And you can do other fun things, right? If you want to develop new protocols, great minds invented this TFO thing. It's pretty old now, over 10 years ago. 15, I don't know, time flies. It's called TCP Fast Open. Cool, fast open. So pretty much a way to send data earlier in the handshake. I told you, ping, pong, ping, a lot of time. So why not send data earlier in that handshake? Cool, TFO was invented. But to do that, you have to set some bits in the header, right? So say, here's a TFO packet. But wait a minute, all those boxes, they know that's supposed to be a 0, never a 1. So A lot of boxes will then just throw away those packets because it's a 1 there that's supposed to be a 0. So TCP fast open becomes the TCP slow open if you try to use it. So the effect of that is not a single operating system enables TFO ever, because it doesn't work across the internet because of those boxes. And I mean, and this story, it's a long story. I could go on. In your home Wi-Fi routers, you cannot introduce another protocol beside TCP and UDP because you can only NAT those protocols, right? If you try to invent a new protocol at this level, beep, won't work. Forget it. It's not going to happen. Someone invented a new way to do compression for HTTP. Cool. Why stick to gzip forever, right? We can invent Brotli. It's much better, at least at some particular kind of data. Sure. So if you do that over clear text, what do you think happens? A lot of boxes, they know compression over HTTP, that means gzip. Yes, it does. So if you try something else, they will sort of ruin your traffic for you. So yeah, I guess you see the pattern here. If they can see the traffic, they will help you. And many, many times, that's not the help you want. So pretty much, this ossification is pretty much make things stop moving. So you cannot do things. You can't keep changing things. There's only one way to change things. Encrypt it. Because if we encrypt it, all those middle boxes cannot see it. They can't understand it. It's just noise through, right? So if it's noise, we can sort of keep changing things. So we want to change the protocols. We want to move ahead with the internet in spite of all these silly boxes, ossification, and everything. So that is what QUIC is, or want to do and is doing. And QUIC is a name, not an acronym. In spite of what you might read on Wikipedia, it started out as an acronym actually, but they removed it. Anyway, it's a new transport protocol, in spite of what I just said, that you can't do that, but you can do it. And when you do a new transport protocol, replace TCP, what do? It turns out that there's a lot of things you can do. You know, this is sort of a demand out there. People finally, after 40 years, we can do a new transport protocol. So what do? We fix a lot of things that we had problems with in TCP. So why not fix that? I told you about the TCP ahead of line block. I'll talk more about that. Why not do all those ping pongs? It takes a really long time to set up a connection. Why? You can fix that. And that TFO thing, send data earlier in the handshake, why not fix that as well? And why bind a connection to an IP address? You know, when you go out from this facility, right, when you have your Wi-Fi and you go out to the cellular network, your mobile phone is going to change IP address, right? What happens to your TCP connections? They're not going to stick, right, because they're bound to the IP address. You have to set up a new one. But why? You don't need that with QUIC. And the key, more encryption, always encryption, and pretty much doing as little as possible in the clear text to sort of reduce the risk that someone in between you and the server actually understand and fiddle and destroy the traffic for you. And ideally, hopefully, crossing fingers, this will allow us to actually keep changing things and improving things in the future. We'll see if that actually ends up true. So this new thing, QUIC, is built on top of UDP. So yeah, we cannot change TCP or UDP. We cannot introduce sort of a neighbor to those. We build on top of it instead. So we pretend UDP is IP pretty much, and build a transport layer on top of that. Sort of replacing TCP and TLS in one chunk, put it on top of UDP. Some have suggested we should call it TCP2, and I think it's fun because one of the QUIC inventors, he used this image once, and I think it's so fun. So in honor of him, Jana. But anyway, so QUIC has streams embedded in the transport protocol in the same way HTTP2 did in the application protocol, but now, so it's basically then a TCP with streams. So we can have many logical flows over a single connection in the transport layer. And you can actually start it from either end, and they can be unidirectional or bidirectional, really cool, and they're independent. And that means that if you set up multiple streams and you lose one of those packets I talked to you about before, the other streams are unaffected, like this. So if you set up a TCP connection, this is a TCP connection. And you send two streams, a red stream and a green stream, right? If you lose one of these, if one of these red packages just drops, the green one has to wait as well because it's a single connection. But when you do it with QUIC and you lose one of the yellow ones, the blue stream can continue because it's independent from the other ones. So only the packages, or rather, only the streams that are in the lost packages are affected by a lost packet. The other streams can continue. Pretty cool, actually. So you can start a transfer and it can complete in the other order because the streams are independent but in order and reliable in themselves. And since this is done on the transport layer, you can do application layers on top of this using streams, becomes for free. You don't have to do just HTTP, you could do whatever. HTTP just happens to be the first protocol done over QUIC, and there are others being made, and there will be many others. This QUIC is certainly here for the long term, and QUIC is going to slowly or eventually replace TCP in a lot of scenarios. You just see. So HTTP1, back to my networking class 101 here. IP, TCP in kernel, typically. Connections in TCP, and then we add stuff on top of that, TLS, and we do HTTP1 like that. And of course, HTTP semantics, what I mean with that is, this stuff you see typically, verbs, methods, headers, data, whatever you see when you use your tools, or watch the traffic in your browser or whatever. So we put in HTTP2 in there. It was a pretty small change. We added streams, compression, server push and stuff. But now we introduce HTTP3. We do it over UDP. And since UDP is the only part here we still have in the kernel space, right? So when we want to do QUIC on top of this, it's going to be in user space. So we get all the connections of streams, and we have TLS inside QUIC. And I'll get back to the TLS crazy situation. And then HTTP3. So and of course, on top of that, HTTP semantics is going to be the same. You're all going to see HTTP the same way as you always seen it, unless you care about what's under the hood. So typically, you don't really have to care, but everything is going to change underneath or between on the wire. Okay. Is it good? Well, the big ones say it's much faster in some situations. And as I told you numerous times now, this is certainly an effort to reduce latency, reduce all those ping pongs and setting up times. So it's much faster in getting that data out early. So setting up a new connection, getting data the first time is much faster. And it's much better in really crappy networks situations, which typically is not for us in this room, because we typically have much better network connections than that. But anyway, a lot of the giants think this is really good for them. It really helps them on the long tail of crappy networks in the world. So how do you get into an HTTP3 world? It's by going over UDP, everything turned even more complicated than before. Right? It's sometimes said that HTTP, or at least people tell me that HTTP is a simple protocol, but it was never simple. It was always really, really complicated, even though you could see it in text once and you could type get blah blah in with telnet, but it was never easy. Doing everything in text and parsing text, finding the end of an HTTP response there's like 4 different ways, and you can always mess it up in some new way. It was never easy, but so doing HTTP2 on top of HTTP1 got more complicated because of all the extra stuff you have to do, but you pretty much have to implement HTTP1 first and then 2 on top of that. And now we add 3 on top of that. So there's a huge building of complexity. But it being UDP also has this fun thing that we have HTTPS://URLs in the world, right? Quite a few. I think. But doesn't that mean they talk TCP, right? So they're everywhere and they talk TCP, but HTTP3 is UDP, or QUIC over UDP. So if you just enter a URL like this, it possibly implies that you need to connect to the TCP port 443 first, blah, blah, blah. Complicated. So the official way to solve this is started out like this. I'll get to what is more. So there's an alt service header. Pretty much you connect to a server, you get a header back that says, oh, I also run HTTP3. You can connect to me with HTTP3 over on this server over here for another n seconds into the future, possibly a year or 2 weeks or 3 hours. So this is, but then you lose a round trip, right? Because you have to connect to your site, old style, get to know, oh, it runs HTTP3 as well. So the next time I connect to this, I can connect with HTTP3. But the next time, right? Pretty much, you don't want to drop your connection now that you have then established over HTTP2, perhaps. So it's a sort of a annoying game because, yeah, sure, next time I can connect to this site with HTTP3. So it's not ideal. So, and it was never ideal, and there are many ways to work around it. I'll tell you about another way that we do it in curl. But this Tuesday, actually, 3 days ago, there was an RFC posted, 9460. This introduces a new DNS record called HTTPS. And the HTTPS is a new DNS record that basically says, this site supports these. It's a really complicated RFC, but one of the ways you can use it is basically to say, this site, you can connect with these different ALPN IDs. ALPN being the TLS extension that you use to negotiate what kind of protocol you speak over it. So you can say, pretty much, you can announce HTTP3 support in DNS with this. So a browser, a client, anyone can connect to your site with HTTP3 on the first attempt without doing the extra round trip with alt service headers and stuff. The browsers already support this. This RFC has been in the works for years. Curl does not support it yet. In curl, we have this fun HTTP3 racing instead. And since it's so fun, I need to tell you about it because we do it like this. So if you run curl like that against a server like that, so when you resolve a host name, for example, curl.se, you get a response, a lot of different IP addresses. Those are actually all genuine IP addresses. We have a lot of IP addresses. When you want to connect them to that server, and you ask curl, use HTTP3, but using HTTP3 is not always working, right? We don't know that it actually supports HTTP3. And HTTP3 is also done over QUIC, right? I'll tell you about that in a second, too. And there's a high risk of failure because there's a lot of organizations that will just block UDP for you. Maybe you're on your company network, and they say, no, UDP is always bad. We only use it for DNS and nothing else. And that happens to a certain degree. So you don't know that QUIC will work. So in curl's case, when you try HTTP3, we start out, try HTTP3 over IPv6. Start that car. And slightly after, we start the second car, H3 over IPv4, because we don't know that IPv6 is faster or better, so we try them both at the same time. And since HTTP3 might not work, we also start the third car here, the HTTP2 over IPv6 car. And HTTP2 car can also negotiate HTTP1, right? Because it's a negotiation there. And of course, you also have the HTTP2 over IPv4 car. And they all race. So the first car to actually establish a connection wins, the other ones are discarded, and that's what we go with. It's a little bit crazy, but it's actually a wonderful way to not have to sacrifice round trips. You don't have to wait. And in a lot of cases, when HTTP3 doesn't work, you really won't notice because they are just a few milliseconds behind. So, and there's also this going into this new network world where we do a lot of things over UDP, we also notice that there are a lot of organizations that not only just block UDP, but many of them are throttling UDP. So UDP is just terribly slow. So that's also a reason why we raise it. So if UDP just happens to be terribly slow, ideally the TCP connection will win instead of the terribly slow UDP, QUIC traffic. Fun stuff. So, HTTP 3 today. These specifications were published a while ago now. As you can see, over a year ago, the last ones. So they're established, they have existed for a while. They're implemented widely by a lot of different libraries and a lot of different implementations in pretty much any language for anything. But it is a challenge, and there's a reason why not all of you are using this like crazy already. And some of those challenges involve what I already sort of alluded to, that connecting quick connections is really difficult, or at least there's a really, really high failure rate because of all those blocking and filtering, and so you have to have a good, solid fallback method. And since you have this fallback method anyway, you want to have that fallback so that it works, and that's not a really good reason for people to stop blocking, right? Because you will hardly even see that you're blocked, because all your browsers are going to just silently fall back to HTTP 2 instead. So most people won't even realize they are blocked, because every client will just magically handle it. So it is crazy CPU intensive, and it's not really visible in my drawings here, but setting up from a client side, you won't really care if it's more CPU intensive or not, because you're using a finite set of connections and a finite set of stuff. But if you run a server and you're already maybe thinking, well, I have my server here, it can saturate maybe blah, blah, 100 gigabits. And what if we then go from H2 to H3? How many gigabits can we use on the same server? Well, roughly a third or something like that. So it's quite expensive in that regard. So we're talking about somewhere in the ballpark of 3 times the CPU performance. And there are many reasons why. And one of the major ones is, of course, that it has a much worse sort of hardware offload story because of all these much more encryption, encrypted in a completely different way than before. So you cannot reuse TLS offloading encryption and stuff. And amusingly enough, the UDP stacks in everything, like everyone is using Linux on the server side, right? But the UDP stack is actually rather crappy for high performance transfers, which is sort of, I think, ironic because it's such a much simpler protocol, but the implementation has been, people have just not done high performance UDP before, so they haven't really bothered about it. The APIs for sending UDP has been really inferior as well, so it really hasn't been worked on enough to become really high performant. So there's a lot of work going on here, so I'm sure that it will improve over time, but 3 times the CPU performance today. And there's this awesome, funny TLS layer. This is a whole separate story I could talk about forever, but I will tell you the summary is that to implement a QUIC, to write your QUIC library, QUIC implementation, you need a new API, you send TLS frames in a new way. TLS was sort of designed to be done over TCP, but this is not TCP. So the great minds thought that we should send TLS in a new way. Since we don't have TCP anymore, we don't have to send them over the same way. So every TLS layer needs to introduce a new API for it to be possible to get used for QUIC purposes, both for the sending and some other of the secrets. And do you think all TLS libraries already have support for this? You would imagine that it would by now, but there's one in particular that does not, and that's the one that everyone is using, and it's called OpenSSL. And they decided, and you can hear that I'm not super happy about their decision, but they think that it is, people proposed a new API, how to do it. They merged that into boring SSL, they merged that into LibreSSL, they merged that into the QUIC TLS fork, they merged that into the AWS fork, but not into OpenSSL. They decided to go another path. So it's difficult to run QUIC then, because the TLS situation is hairy. All QUIC stacks are also user-land, so there's no standard QUIC API, so you pretty much have to get married to one particular solution. So it's not ideal. And not the least, I mean, we have used TCP for a while, right? Everyone has used TCP dump or Wireshark or something, at least some point in time. And you know, segments, windows, blah, 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 you can read about. Forget about that. This is not TCP anymore. And it's encrypted all the time, right? So how do you even snoop on all those traffic situations? So you need new tools. Okay, Wireshark is, of course, on track. You can use Wireshark, but you also need those, you know, SSL keylog tricks to be able to snoop on the encrypted traffic. And yeah, it's a new paradigm in tooling and understanding your connections too. So it's a challenge there as well. All browsers support HTTP3 since a long time, and they all speak HTTP3 to a very high degree already today. So the only good data that is available for that is if I can check how much HTTP3 the Firefox is doing in their beta releases. And as you can see, 27% of all requests Firefox users are doing is HTTP3. Quite a large number, I'd say. And if you check it the other way around and check what do websites support, well, 27, it's the same number, right? 27% of all top websites also support HTTP3. So it's way more than, it's over a quarter of all the web traffic from both ends, right? Maybe what's interesting also that this graph shows a year back. It comes from this site, W3Tex, and it's pretty stable. It hasn't really moved. You can think about why that is. The HTTP2 is going down, but HTTP3 is pretty much stuck there. And even if I go to a third site and check it out, like Cloudflare, I mean, they host a lot of stuff, right? So they're possibly a good source to show how much people are actually using HTTP3 hosted by Cloudflare, and that's even more than. But similarly, it's rather stable. It's not moving a lot. And I think a lot of explanations, of course, it's so expensive to run it, it's so complicated to run it. HTTP3 then being encrypted all the time over UDP, it looks exactly like just a massive DDoS, right, on the traffic. It's just random noise over UDP. Everyone who is big on the internet runs HTTP3. That's why pretty much 27% of the web means you're talking to one of the giants, like these Facebook, Instagram, and on the Google sites, some of the Microsoft sites, all the big CDNs. And pretty much, I guess that is, yes, that's 27%. And very few smaller players run it, because I think because of complications in running and doing things. So, okay, when you want to play with it in curl, because you do, right? We are going to ship it as a sort of, the next release is going to be the first release with curl that when we ship HTTP3 that is not experimental. So it's taken us a long time. And the reason is that we're using third-party libraries that have been in beta versions until now. So complicated. And we support alt service, and I showed you about the fundraising thing we do. We support several different backends, and I'll show you how it works, because why not? In curl, we like to just support everything, many different things. So pretty much, when you run curl and you want to do HTTP3, we have 3 different implementations in parallel. Just so you can go with this is a library called NG HTTP3, made by the same team who made NG HTTP2 before. There's also a Microsoft solution. Well, the guy who writes it works for Microsoft. I don't think it's an official Microsoft solution yet. And Cloudflare makes a third library, Quiche, that's written in Rust. The other 2 are in C. So you can go with either one of those. And what's fun is that the Quiche one then is both HTTP3 and QUIC. And the other ones are then using QUIC libraries. So you have HTTP3 libraries that are using QUIC libraries, NGTCP2 or MS-QUIC, and they are then in themselves using TLS libraries. And as I told you about TLS, right? They are using, so if you want to go with TLS, for example, if you want to go with the third solution, want to go with NG, HTTP3, NG, TCP2, and the TLS library, you go with the fork family. That's my name of that fun family, which does not include OpenSSL. So So if you want to go with HTTP3, you cannot go with that, but you can go with a lot of other solutions. So you can pretty much go with pretty much any other TLS library than OpenSSL. And also, of course, the other solutions then also sort of supports a different set of TLS libraries. Fun stuff. People are asking me why you can keep on working on curl still, but you know, this is how. Yes, fun stuff. But what I wanted to say that so the NG HTTP3 solution here, the tall one with the most support for different TLS libraries, that's the solution we're going non-experimental in the next release, and that's really the solution I recommend because it's the most solid one, stable one. It works. It has been working for quite a while, so it performs and works really well. Yes. So pretty much what you can take away from my blabbing today is that HTTP1 is sort of old, is ineffective use of TCP. Pretty much TCP never gets up to speed properly before we close down connections. And you do a browser situation at least typically do a lot of parallel connections. And HTTP2 was introduced as a way to combat the problems with one, and instead we introduced a new fun problem called TCP head-of-line blocking. It's a problem mostly for people with worse network connections. So if you have a really good network connection, you pretty much won't see any difference between 2 and 3. But if you have a bad network connection, 3 is really the way to go. It's done over QUIC. QUIC being the new way to do, sort of, is going to phase out TCP over time. We're going to talk more to QUIC in the future. Fewer round trips, a lot fewer round trips, as little as 0 actually in many cases, and individual streams over connections. That's it. Thank you. Easy peasy.